Well, hello, everyone. Thank you so much for attending today's webinar, How Digital Twins Power More Sustainable, Resilient States and Cities, especially given that it's also the ESRI conference this week. So we really appreciate all of your attendance. My name is Amy, and I am the operations manager here at National States Geographic Information Council. If you are unfamiliar with our organization, NSGIC exists to advance effective national coordination of geospatial information by supporting state-level cooperation. We serve as a national forum for the development of capable and future-oriented geospatial leadership. If you'd like to learn more information on how to get involved with us, please visit our website, www.nsgic.org. I will pop that in the address chat box shortly. Just some reminders for today's call. All attendees have been muted on entrance. There will be time at the end of the presentation for Q&A, so please place your questions into the chat box and they will be read aloud later at the end of the presentation. Additionally, a recorded version of this webinar will be made available afterwards, so be on the lookout for an email with that info. And with that, I'd like to turn it over to today's presenter. Travis?
Thanks, Amy. So my name is Travis Gelati. I'm the Director of Content Technical Solutions and the Product Manager for Hexagon's content program. Over the course of this presentation, I will take you quickly through the content program itself, for those of you that may not be familiar, and I'll discuss some of our recent innovations and applications that help power resilient states and cities. So with that, I will turn off my video and we can get started. So like most organizations here at Hexagon, we're focused on the autonomy of things. And the road to autonomy for us has largely been enabled by our unique set of core capabilities. So I want to take a little bit of time to set the stage so that you can take confidence in what we believe are the new opportunities for imagery products as they relate to state and city resiliency. So for many years, Hexagon has been modeling the physical world into digital representations at pretty much every level. Our Leica Geosystems terrestrial, mobile, and aerial sensors are globally recognized as best in class, and we've built corresponding software systems that allow the data to be accurately and precisely located, processed, and visualized to glean actionable information to solve a broad range of customer challenges. So going beyond that, we've identified and developed not only the means to provide the highest data integrity, but also how our sensor data works between our own sensors with external sensors, and then how best to integrate our data to solve unique and cutting edge applications. In the geospatial content systems department, which I'm located, our legacy has always been linked to data. We emerged as a leader in sensor solutions nearly 20 years ago in the film industry. That enabled the digital capture and positioning of the physical world eventually when that revolution took place. We added sensor solutions to not only unlock the value of our sensor data, but to also offer the ability to design, simulate, provide locational intelligence in real world scenarios. And today we're combining things like machine learning and AI with our sensor and software leadership to create powerful autonomous solutions. As we forge ahead, we'll continue to put all the pieces and parts together to drive the digital twin initiative from every level. That involves reality capture and positioning technologies, which enable the structural and attribute components of the physical world, and then the translation of them to digital representations for further use and exploitation. The data and derivative products that we provide are shifting further away from abstraction, which we've seen in the past, to represent more reality. And the locational intelligence inherent in our data enables active geo-reference situational awareness for a multitude of applications. Finally, our continuous push towards autonomous technologies means that we're able to provide and produce the best data efficiently and effectively the first time, which keeps our costs low to the market. We're thereby able to produce the most detailed level of data across expansive and required geographic regions that our industry demands. I'd like to begin the core of this presentation by discussing the background of the Hexagon content program and some of the recent innovations in sensor solutions and the subsequent data products, and then also get to some applications which currently use the data. This slide outlines some of the emerging trends that we're seeing in the geospatial industry. that will allow us to outline and how we grow along with our industries and customers. We're seeing demands in capturing larger areas of increasingly higher resolution imagery and LiDAR point densities with higher refresh frequencies, all for a lower price and reduced environmental impacts. From a sensor development, acquisition, and data delivery perspective, the industry is being forced to seek productive and productivity and deliver via creative business models that benefit our customers. With this comes a focus on delivering products and services that are driven by automated processing, which increases the efficiency and consistency of the derivative product generation, meaning a faster delivery of our products to the market, and thus faster refresh in the future to satisfy the growing demands of the industry that continually change in need and desire. To grow with and satisfy the industry, we'll need to respond to all of the above factors, and that's currently what we're doing. And this drives our innovation and market entry points to support the overall geospatial industry, which also benefits you as customers and potential customers. So how do we respond to this? Well, firstly, we build and integrate sensors like our content mapper and our city mapper, which you may be familiar with, which allow us to see tremendous gains in productivity in delivering the wide-ranging multi-purpose data in a variety of ways to the market. So as mentioned, the Leica Geosystems Content Mapper is one such advancement that allows us to respond to the growing need of larger acquisition areas with higher resolutions and refresh. The Content Mapper provides increased flexibility in acquisition operations, which allows us double the coverage at the current resolution or double the resolution at current flying heights. This means higher resolutions over wider areas, increased flight efficiencies, especially during the leaf-off season that can be traditionally tighter acquisition windows, and or increased refresh rates to satisfy the needs for change detection or other applications in the market. The Content Mapper is also what's going to allow us to effectively transition from capturing state-level data at 30 centimeter resolution to 15 centimeter resolution in the coming years. I'm happy to report that the Content Mapper is currently in operation in many states and will continue to grow in usage over the current acquisition season. As most of you are probably aware, our mature workflows produce the highest level of photogrammetric and radiometric quality, as well as our efficiently planned acquisitions over the course of a single season mean highly consistent data that is ideal for base mapping and visualization, and even the most advanced machine learning and AI applications. It's important to note, and what I've alluded to in some of the previous slides, is that we as Leica Hexagon control the entire workflow, from building and integrating the sensors into our aircraft, planning the data collection missions, and then finally processing that data with our own software and then delivering that data to the market or to customers specifically. Our off-the-shelf products include 4-band multispectral data at 1 foot and 6-inch GSDs. And like I said, we're hoping that in our next refresh cycle in the coming years, we're going to transition most of those 1 foot statewide coverages to 6-inch coverages. As always, our image data can be purchased directly through our online store or streamed directly into a variety of GIS software and custom applications via WMS and WMTS protocols. In addition to our imagery products, we also offer imagery-derived elevation data, or DSMs, which have been growing in popularity by leaps and bounds recently. We offer DSMs at both the 6-inch and 1 foot levels, and those can be delivered in point cloud or raster formats. If you are unfamiliar, the Hexagon Content Program provides 100% complete coverage of the US. That means just about over 6 million square miles of 30 centimeter resolution data and 1 million square miles at 15 centimeters or 6-inch resolution. In 2021, we added just over 1 million square miles of data to these totals through the refresh of 19 states. And in 2022, we'll refresh 9 states, which will add approximately 1.3 million square miles to the program. All of the 2022 data will be added at 6-inch resolution to join our current 6-inch states of Washington, Utah, North Dakota, Delaware, Louisiana, and Texas. This slide just reiterates and shows our current 6-inch coverage states. As you can see, Texas was collected in 2020, and currently we're refreshing those urban areas this year in 2022. All of the dark blue states we're currently acquiring this year, which will start to be available at the end of 2022 and into early 2023. So how do we do all this? Hexagon's tremendous amount of aerial assets, coupled with our network acquisition partners, provide data collection volumes that are second to none, while our various distributed data centers in North America, Europe, and Asia minimize their product delivery turnaround times. We also have a large group of authorized resellers, which mean our data can be further customized to your needs. So, we currently stream about 1 billion images per month. So our data library and storage and databases are quite extensive. So here we see examples of our 6-inch imagery data. This is 4-band imagery, and thus can be spectrally represented as either a natural color RGB representation or as a color infrared using the near-infrared channel. On the far right of the slide, we see the corresponding elevation data that is photogrammetrically derived from the imagery during processing for each pixel. So as you can see from this combination of data, we're building sort of the quote-unquote digital twin at this wide-ranging data coverage areas from coast to coast. So a further strength of the image acquisition and processing approach is that all of the derived image products correspond exactly and thus create a robust data set for further exploitation and analysis. Here we see our standard RGB data overlaid on an elevation data set, a 2D surface model derived from the imagery, point cloud data encoded with RGB values, that data segmented for elevation, and then that data classified as well. Just discussing height data a little further, we feel that the additional information helps with better artificial intelligence inference, better accuracy and change detection, and also allows us to perform more highly automated vegetation analysis and biomass evaluation. The faster access to 3D land use data from AI also allows updating of the 2D building cadastre from 2.5D to full 3D representation. Since we're on the topic of wide area acquisition to start, we'll take a closer look at the cross-section of current applications that rely upon this data. So our data is currently being used over a variety of industries and applications, with the limits really only set by the imaginations of the industry users. Our customers benefit from our broad area coverages, as well as the ability to access our imagery via either custom orders, which are served through our extensive production teams, or more recently and more importantly, streamed directly in their traditional GIS or image processing softwares or custom feature extraction applications through a data subscription. The ability to access our large stores of data without the overhead of purchasing, owning, or managing the IT infrastructure makes our data more relevant by broadening the access for the limited time an organization may need it. Our licensing models can be set up through measured usage or consumption as well. So, as such, our data is easily available by all, not only the larger mapping centric organizations. So as pictured here, the third dimension adds a wealth of information to really any analysis. This is the accompanying DSM data that we have with our imagery. So here we see the ability to monitor a right-of-way from the comfort of our office, as opposed to sending costly field crews out to assess the data. You can even see some infrastructure outlined in that surface model as well. The ability to encode this data with color infrared information allows us to extend the analysis for vegetation health to identify trees which may pose a risk, or by elevation to make quick and accurate measurements of the tallest trees that may reach a power line or asset should a fall event occur. This is an add-on to the previous vegetation slides. The extracted information can then be added to mapping platforms to summarize the data. So here we see a dashboard of some analytical work, and this can be pulled directly from our content library or processed databases here at Hexagon through our services organization, so that organizations can use the data without necessarily being burdened with the overhead associated with storage and analysis. So here we see some tree identification and tree crown information that's been identified and overlaid on a viewing platform to provide a little bit more gleaned information from the data. Similarly, land cover and land use can be classified in the results ingested through workflows to provide a summary of the data via dashboards for reporting that can be easily monitored by multiple groups, or for more informed decision making on organization specific projects. With digital twins, areas are made to be machine readable with the help of algorithms. And we can see here how much water is spreading so that we're better prepared for heavy rain events. As most of you are aware, it's predicted that heavy rain events will be more intense and the probability of the occurrence will increase. The data can now be used in such a way to benefit those forecasting across large areas due to our immense data coverage, either at the state level, the county level, or even the country level. This is another typical example of how our data can be exploited at scale. Here we see that roads, center lines, and markings can be extracted from the imagery. Another interesting thing to note is we've recently partnered with AI-derived product company Acopia, located in Toronto, Ontario, Canada. And Acopia is currently mining our raw data to derive a myriad of 2D and 3D products that we're seeing having wide-ranging applications within many state governments and municipalities. Acopia's advanced AI algorithms automatically detect and extract a variety of features from the imagery. So here we see land cover, land use, sidewalks, crosswalks, and parking lots, as well as road center lines that are being used for transportation studies, vision zero, and right-of-way analysis. Further, Acopia is working to create 3D products as well. The identification and mapping of these urban features, such as buildings, are important tasks for the industry in general, but for smart cities and urban planners, as the building footprints can aid risk analysis. The three-dimensional representations can provide a line of sight for future development planning and visualization, just to name a few. This partnership is of significant importance as all of these extended feature data sets accompany the delivery of new states we add to our existing libraries. The image data gets updated, so do the featured data sets that perfectly align with our data. So it's really a 2-for-1 that's being created and offered here. Here's another example provided by our partners at Blue Sky. We're now seeing more and more remote infrastructure assessment. And this specific example shows road crack detection from our high resolution imagery. Further from Blue Sky, urban tree canopy extraction, tree counts, and tree height models are helping to manage stormwater runoff, air quality, heat waves, and environmental health. We see here a solar potential analysis that was completed on our digital surface model data. Another customer, Land Info, uses our data extensively to support the 5G engineering industry and their continued rollout of high-speed internet. In this slide, we see products such as land cover, building, and tree models that are being used for siting, placement, and signal propagation to support the needs of that industry. And finally, at the end of the day, we are a data provider. All of our data are provided in formats with the appropriate metadata so that third-party users can easily integrate our data into any software package or application of their liking. Here we see our data being integrated and exploited in the Esri platform. We're seeing extractions of parcel and building and swimming pool polygons, as well as line-based street layers and a vegetated land cover type. So that is the background and some of the use cases involving our countrywide data sets. At this point, I'd like to turn our attention to our Metro HD program, if you're not familiar, that is focused on acquiring higher resolution data and derived image data products in the city or the greater metropolitan areas. As you'll see, this data is produced in both 2D and 3D formats using largely automated routines and delivered at very high resolution. So the workhorse in the Metro HD program is our City Mapper 2 sensor. This is a follow-on to our City Mapper 1 sensor that was developed in 2016. So while this may seem like a new concept, it's certainly not a new technology. It's important to note that the City Mapper 2 is a hybrid acquisition system and it's composed of subsystems that are world-class on their own. So the CityMapper 2 involves a mixture of 2 image capacities. That's our 150 megapixel passive imaging sensors and the 2 megahertz Hyperion 2 Plus LiDAR system that's found in our terrain mapper sensors, if you're familiar with that product line. Again, this is not a LiDAR sensor with a camera to provide context only. These are 2 well-defined and popular products from the Leica family that have been combined and optimized for superior performance for a variety of applications. And this ultimately strengthens the resultant data products we're able to leverage based upon the strength of each system. So you can see the CityMapper 2 sensor on the left. In the middle here, we have our 2 megahertz LiDAR sensor. We have 2 nadir looking cameras, and then we have 4 oblique sensors as well. In the middle of the slide, you see the footprint and the middle swath of the LiDAR data that corresponds with some of the imagery in that pass. And then from that sensor, we're able to output a variety of what I consider are more raw data products, which is intensity, elevation, and all that data can be, LiDAR data can be spectrally encoded with RGB or color infrared. And then, the imagery output, which is really focused on the raw data frames, and then some standard orthorectified image deliverables as well. So beyond sort of the raw data that comes out of the sensor, this slide shows what I consider to be our core image-derived data products. So we see in the upper left-hand corner the oblique and nadir imagery frames, which is delivered at the native resolution of the Metro HD program, and that's at 5 centimeters, or approximately 2.5 inches. LiDAR data encoded with the spectral response of the RGB or the color infrared cameras. This has a 10 centimeter RMSEZ and a 20 point per square meter density, and those are delivered in LAS and LAZ formats. Next, we have our DSM and DEM data layers. These are delivered at 15 centimeter resolution, and these are derived from first return and last return LiDAR, respectively. And finally, a standard 4-band ortho data set that is delivered at 2.5 or 2 inches resolution over by a 1K by 1K image format tiling structure. I use the term standard here because the data set contains the radial displacement of objects above ground, as is found in most orthorectified imagery offerings on the market. And this imagery can be delivered in a variety of common image formats, including GeoTIFF, PNG, and JPEG. Moving on in our Metro HD data program offerings, listed here are the imagery-derived data sets that are automatically produced through our advanced AI-based workflow. All of these data sets are produced in parallel, and so you can imagine are quite data intensive. In the upper left-hand corner, we see probably the most popular product, the aerial mesh model. This data product is essentially a mesh of triangulated structures derived from LiDAR and photogrammetric derived structures, similar to a tin model that you may be familiar with. And these are textured using the corresponding oblique data. The data can be delivered as 3D tiles, OBJ format, and then SLPK format that's adjustable into Esri products. Moving to the right, we see the true ortho data product. So in contrast to the standard orthorectified data, the true ortho product positions each pixel as if viewed directly from above in its true orthographic position. And since no obscuration to the ground exists in this data, it's an excellent source for deriving building footprints and extracting a variety of features. Similar to the standard ortho data set, this is delivered as a 4-band data product at 2-inch resolution. Moving on, we see our semantic and 3D data layers. We have an LOD2 building layer, which you see in the upper right corner. We have a 20 to 25 land cover class layer that's automatically derived using our global database of training data. And then we have a 3-dimensional tree model as well. We have some accompanying data with the tree model that includes the location and the size of the crown and the volumes as well. So I want to spend a little bit time taking a deeper dive into the hybrid acquisition approach, if you're not familiar, and why we believe this is the superior method for reality capture in the digital twin space. So first, we generate superior level data. On the left are some images representative of our forward motion compensation technology, which allows us to collect superior imagery even in low light conditions at the fastest aircraft speeds possible, which maximizes collection, especially over a city or urban environment where there's multitudes of differing light levels created by not only the sun angle, but the positioning of buildings as well. So you can see in the images on the left, these were captured at a less than optimal time of the year, very low sun angle, below 30 degrees, as you can see in the long objects, shadows, even over the relatively lower height objects. The image was acquired at really fast speeds with a pretty long exposure interval in terms of aerial acquisition. So to reduce the motion blur that you see in the upper image without forward motion compensation, we'd either have to dramatically reduce the exposure time, which could add a lot of noise to the imagery, or slow the aircraft. In this case, forward motion compensation lets us avoid this compromise and obtain the best image quality possible and a nice image as we see in the lower representation. So this allows us for a wider range of acquisition times and duration, as well as helping us combat the low light conditions in the urban canyons, which I just mentioned. So further from the passive imaging side of things, the Hyperion LiDAR employs a circular scan pattern. This helps us in city modeling by providing both a forward and backward look angle and not simply sideways. This aids the volume of data capture on vertical surfaces. It allows for a bit of a more even point distribution, which allows us to capture and then ultimately model the facades of objects, which is really important when we're talking about the urban environment. It also means that we don't have to fly additional perpendicular flight lines to capture that data, which means lower acquisition costs. So if we look at the images on the right side, we see a cross section through the data in the upper image, and we see that point representation slice in the lower image. You can see that there's a good amount of data, not only on the top surface points, but also on the sides and facades of buildings. So let's go a little bit further in this. So currently in the market, we're seeing organizations that are using imagery only as the foundation for city modeling. We believe, and it's been shown in research and investigation, that the introduction of LiDAR really increases the accuracy of the data and the robustness of the reconstruction. Simply stated, at the end of the day, having LiDAR and imagery provides us the opportunity to use the best and most comprehensive, measurements, which includes the XY plane from imagery, the Z component from LiDAR, stronger top surface models from imagery, which the density of those point clouds are often based upon the image resolution, which can be a little bit denser than LiDAR. Since we're moving beyond the passive system and integrating the active system as well, we're able to operate more effectively in shadow environments and in areas where the ground may be occluded by building geometry and unable to find two or more representations of that ground or object point feature, which is required for stereo photogrammetry. And then finally, we get vegetation penetration as well from the LiDAR data. And then, finally, having image data we find is much better for interpretation, context, material surface identification, and classification of the data. And because we have 4 bands, including near infrared, we can extend the calculation to vegetation indices, and this can be extremely helpful as we see a number of cities attempting to characterize their vegetation for general landscape in urban planning. Acquiring multimodal data with optimized and core-bore-sighted instruments is of tremendous benefit to the products that can be generated. No longer do we have any limitations because the data is not aligned or lacking in accuracy of a certain dimension, but it goes further than that with the integration of LiDAR and imagery together. So let's take a look at some of the inconsistencies in model data that are alleviated through the hybrid acquisition. Point clouds generated from imaging only, as I talked about in the previous slides, even if flown with dense overlaps, still show problem areas where point extraction is not good enough. And this is due to an inability to confidently match those pixels, which again is a requirement of stereo photogrammetry. So occlusions in canyon areas, not only do we see impacts by shadow, but also building geometry, occluding some of the ground surfaces in imagery acquisition alone. Non-textured surfaces, sometimes these areas can confuse the 3D reconstruction algorithms based upon traditional stereo photogrammetry. We have vegetation penetration as well, as I alluded to in the previous slides, and then shadow areas. These are all areas where LiDAR really helps the reconstruction of the data by adding robustness and strengths to the raw data and the data products we can derive. So here's an example of the power of a combined hybrid data set. Noticeable are the full representation of even the most delicate structures, as well as the fullness of the tree canopies. And the ability to encode the LiDAR data with concurrently collected imagery data is another huge benefit of this approach as the data interpretation is vastly improved. So here we can see how the roots of the LiDAR and imagery together help the extension to advanced modeling and what LiDAR can bring to urban mapping. So here we have some reconstructed urban models. On the left side is an image-only representation. On the right side is imagery plus LiDAR. So we can start on the vertical facades of the building shown on the left. You see it's a bit roughly modeled. With the inclusion of LiDAR, we're able to provide a more consistent and flat planar surface. Again, occlusions in canyon areas. Again, we see some deficiencies in the modeling, and we see a much better representation when we add LiDAR to it. And then again, in areas that are traditionally impacted by shadow, we're able to clean up some of that modeling data as well. So here, in the final product, we see a tremendous detail at the ground level in our models. And as we pull up, we get a better view of the data. And the thing that I want to mention here is, this can all be done at scale. It's not a localized data set. We're producing all of these data products at wide geographic regions. And then with the wide-ranging data products that we're able to deliver, we have a broad and diverse and still evolving opportunities that we're currently seeing. We see our data being used to support a variety of market opportunities in visualization and simulation, as well as providing our customers with enhanced decision-making and cost savings through reduced site visits. So let's get to a little bit of the visualizations and some of the eye candy from this data. So the integration of LiDAR data going beyond what we just showed allows us to better integrate our data with other passive and active data because the geometry is right. LiDAR really provides that robustness and strength in the data. So here we see the results of our partnership with Cyclomedia, where we've taken our aerial mesh to the next level through the integration of mobile scanning data for the terrestrial portions of the data. So this has the advantage of being able to see the city in all of its detail from both above and below, under tree canopies, etc. So we get to an even closer, full representation of the scene. In this short video clip, we see our aerial mesh data being leveraged for wind modeling. The details and structure of the scene really provide an enhanced benefit. So not only are we just looking at simplified blocks or generalized data, we're looking at the full representation of the reality, which can improve the results. So, not too far off in the future, and some of the things that we're working on now will be to explore better ways to characterize the material of the structures, which will take these simulations to even the next level. Here we see a line of sight analysis that once again benefits from our 3D aerial mesh data. Like in the last example, characterizing the material benefits these analysis as we can further explore how RF signals or perhaps even GPS signals will be impacted not only by the structures, but the material of those structures. So just further moving on to the integration of data, we're seeing here our aerial point cloud data being integrated with mobile LiDAR and scanning data. So we're able to take the top surface models, which are created through aerial mesh, from the aerial acquisition, and then integrating below surface data as well. This is because the data that we're producing is so structurally sound to begin with. And then the last visualization here is once again just to reiterate that we're producing this data at scale. So here's an entire city area in Europe where the data has been able to be classified and then thus used to extract features or to perform higher level data visualizations or analysis of those scene objects. And so we're also working on a myriad of ways to deliver this data to our customers efficiently without the high overhead costs of transferring and storing the data. This is culminated in our Hexagon digital reality platform, or HXDR for short. This is a cloud-based platform that will soon replace our current online data stores for data purchase, as well as offering a greater access to and visualization of all of our data for use by our customers, for even cross-organization collaboration and manipulation of the data. So this is something that will be coming in the near-term future. And so with that, I'd like to conclude today's presentation. As always, I appreciate your time and attention and consideration of the materials presented.
Thank you, Travis, for that presentation. It looks like we have a question in the chat box. Let me make sure this, and anyone else who would like to ask questions, please put them in the chat box now and they'll be read aloud by me. John asked, are you removing people from the imagery? I don't see any people in the city.
Yeah, that's one of the things that we remove from the data sets. That's correct. Yep. And that's handled through an automated process.
We'll give folks a minute if there's any more. Tim asked, do you create models as a service?
We certainly can go down that path, and we certainly do that for a variety of organizations. So we're willing to entertain that. Mostly we're focused on acquiring data sets and then adding them to the content library, but we're always willing to hear of exciting projects that can benefit from our sensors and processing strategies.
Well, if there aren't any more questions, Travis, thank you so much again for this presentation. Would you like to add any last words?
No, I think I'm good. I think everybody should just enjoy the rest of their day, and it was a pleasure presenting to everyone.
Thank you so much again for coming on and giving your time. A wonderful presentation. And thank you again to all of our audience for participating today. And just a reminder, this is recorded and will be sent out later for your viewing pleasure. Thank you so much, everyone. Y'all have a great day.